Alright, so building off of part 1 of the framing topic, once you have the basic contours and structure complete, you can begin synergizing what needs to be done so it gets done quicker with reduced hiccups. And that all begins with roughing and mechanical items, particularly HVAC and plumbing, since the former requires the most space and they both feature components that run through the roof line that will require flashing while the roofing is being done. The rough-ins quite simply embed the main components of each system in between the frame members of the house, so the overlay, namely insulation, vapor protection, and drywall contributed soon after can cover and protect them thoroughly. Now, I'll spend more time on each individual rough-in in later videos, but for now we're focused on, of course, making sure everything is situated in a manner that works optimally with the subsequent room designs. Feeds running along the exterior wall require being boxed in so the insulation and vapor barrier can be placed on the inside, while beams and joists running perpendicular to the heating result in the same. After the critical rough-ins have taken place, you can begin roofing the home, and this is an item I prefer taking on before the installation of windows merely because it eliminates the chance of having fallen debris destroy or damage the glass and its casement. Particularly if you're working with heavier materials such as clay or slate, or elaborate made-to-order designs that are considerably higher along the price spectrum. So honor roofing at a rudimentary level consists of an underlayment, which is typically a protective asphalt saturated felt, which is designed to repel water but yet still allow air passage through, followed by courses shingle, shakes, or whatever other material you choose that are overlap particular dimensions to allow the water to travel over towards the area where the roof terminates, where they are then assisted by drip edges, which rest under the whole assembly just on top of the plywood sheeting, sealing the deck with the fascia board and directing water away from the home towards the east troughs and downspout. Now, all flashing, which is usually made of thin galvanized steel or neoprene rubber in circular regions like around the stack vent, are designed to protect seams that take on a high volume of water or that may be more prone to buildup, such as extrusions, valleys, as well as roof ends. Now, most of the roofs you see in North America are asphalt shingle roofs, which are actually fiberglass matte asphalt top shingles, which are rated for approximately 15 to 30 years. Proceeding on to windows, it's important to remember that glass tends to be the most vulnerable area to fire, wind, damage, as well as the biggest source of heat loss. In fact, in some cases, poorly insulated windows and doors can account for as much as 25% of your energy bill. So there are maximum ratios of glazed openings on exposed surfaces that are permitted for particular fire and heating situations. With all this being deposited, there are certainly technical elements embedded in the material design that aid desirably high levels of natural light without promoting as much energy loss. Contemporary windows feature low emittance coatings on the interior side of the glass that reflects most of the long wave heat energy initiated by the sun while still permitting the passage of short wave visible light. This, teamed with the inert gas sandwiched between the double panes of glass, which is heavier as well as less conductive than air, assures the heat gain or loss through the window converges with the thermal efficiency requirements alluded to in the building code. Now, all this critical information is available on the Windows Energy Performance label, which highlights things like the product's U factor, which gauges the rate at which the unit conducts heat per hour in the form of a decimal. And this is simply the inverse or mathematical reciprocal of the more familiar R value, which measures an insulating material's resistance to thermal conductivity at a given thickness. So if you have a 20mm window rated at roughly R3, you know the material elevates thermal resistance by 3 times, thus allowing 0.3 of the proximate heat to travel through per hour. Once the window layout and their composition is out of the way, the installation begins with the house wrap being cut down the middle and tacked back into the frame on each side, with the top portion folded up until later. Flexible flashing, which comes in a tape-like form, is adhered around the bottom end on top of a sill pad, and the flanges of the windows are coated with sealant and placed in the rough opening. Shims are added if needed to square and plumb the window, and then the flanges are covered with flexible flashing tape as well, while at the top a drip cap is sealed and tacked onto the wall with a strip of flashing tape layered over it. The portion of the house wrap that was folded up initially is brought back down and is skip taped over. Now, the reason the top is done like this is similar to the roofs. We're trying to protect against water by layering materials so any troublesome runoff is directed from the structure instead of being guided within small seams and voids between the materials. Once these 3 items, the rough-in, roofing, as well as windows have been completed, you can then confidently move on to the next stages of construction, which I will of course be going over in upcoming videos. For now, like always, thanks for watching. This video was a lot of fun to make, and we're getting there on our nice little home creation journey, so stay tuned for what's next.